Okay, so today we're going to dive into what is honestly one of the most powerful and, frankly, beautiful ideas in all of statistics.
You've definitely seen this shape before, right? The bell curve. It shows up in nature, in finance, in your test scores. I mean, it is practically everywhere. From the heights of trees to the tiny errors in scientific measurements, this pattern, the normal distribution, just appears again and again. But why? What is the fundamental rule of the universe that creates this exact same shape over and over?
Well, the secret is actually way simpler than you might think. It all comes down to a process that's happening all around us all the time, just adding things together. So instead of me just reading you a dry definition of the theorem that explains all this, we're going to do something better. We're going to build it from the ground up and discover it for ourselves.
All right, so let's start with a really simple experiment. We're going to see firsthand how just adding random stuff together can create a very specific, predictable shape. And we'll start with the most basic, most un-bell-like shape you can possibly imagine.
Okay, check this out. We start with a single random variable that has a totally flat, uniform distribution. What does that mean? Just that every outcome is equally likely. Kinda boring, right? But now, watch what happens when we add a second identical random variable to it. Bam! Their sum isn't flat anymore. It's a triangle. All of a sudden, the outcomes in the middle are way more likely than the ones at the edges.
And this is where the magic really starts to happen. As we keep adding more and more of these variables together, the shape of their sum just keeps evolving. When we're summing up 10 of them, our triangle starts to get these kind of rounded shoulders. And by the time we're summing 30 variables, wow, the shape is totally morphed into that unmistakable, elegant bell curve.
So seeing this is super cool, but for it to be actually useful, we have to be able to describe it with math. Our goal here is to find a way to handle this sum so that as we add more and more variables, its shape doesn't just spread out and disappear, but actually settles down or converges to a single, stable form. So our first instinct, the most obvious approach, is to just look at the simple sum. We'll call it S sub n. Makes sense, right? We're adding things up, so let's just track the total sum and see what it does.
Now, the key thing we need to watch here is the variance. You can just think of that as a measure of how spread out our shape is. How wide is it? So let's see what happens to that width as n, our number of variables, gets really, really big.
And here's our first problem. The variance of the sum is just n times the variance of a single variable. That means as we add more variables, the variance just explodes. The distribution gets wider and wider and wider, spreading itself out towards infinity.
So yeah, attempt number 1 is a total failure. Instead of converging to a nice clean shape, our distribution just flattens out across the entire number line until it's basically invisible. It doesn't settle down, it just disappears.
Okay, attempt 1 was a bust. Maybe we went too extreme. So what if we try to rein it in? Instead of the raw sum, let's look at the average. We'll just divide our sum by n. The average, that's got to be more stable, right? Well, now we have the exact opposite problem. The variance of the average is the original variance divided by n. So as n gets huge, the variance shrinks down towards 0. Our distribution just gets squeezed tighter and tighter into an infinitely narrow spike.
And another failure. We went from a distribution that flattens into nothing to one that collapses into a single point. We've totally overcorrected. Our beautiful bell shape has been completely crushed. We need something in between.
So, not scaling at all was too little. Scaling by n was way too much. What if we try something right in the middle? Not n, but the square root of n. Maybe this is our just right Goldilocks solution.
And wow, this is a huge step forward. But it also reveals a brand new problem. We solved the variance issue. By dividing by the square root of n, the variance is now perfectly stable. Awesome. The problem? Uh-oh, look at the mean. It's drifting away to infinity. We've stabilized the shape, but now the whole thing is just sliding away from us down the number line.
Okay, this is it. Let's move to the final step that puts it all together. We figured out how to make the width stable. Now we just need to nail down its location. And the key is to solve these problems one at a time in the right order.
The big breakthrough is this elegant two-step process. First, before we do any scaling, we lock the center of the distribution at 0 by subtracting the mean of the sum. Then, and only then, after it's centered, we apply our special square root scaling factor to get the width just right.
And here's the magic. This new variable we've built,
this z sub n, it's perfect. No matter how many variables we add, 10, 1,000, a million, its mean is always 0 and its variance is always 1. It's stable. It's predictable. It is exactly what we were looking for this whole time. And success! We finally solved the puzzle. Through this process of first centering and then scaling, we have perfectly engineered a variable whose distribution doesn't fly apart, doesn't collapse, and doesn't drift away. It will finally settle down into one consistent, beautiful shape.
So, after all that work, what's the big payoff? We found this perfectly stable variable, but why is this considered one of the most important, most fundamental theorems in all of statistics?
Well, this is the formal statement of the central limit theorem. And it says that the distribution of our specially constructed variable, Zn, becomes the standard normal distribution, that perfect bell curve with a mean of 0 and a variance of 1.
And here's the truly powerful part. It doesn't matter what shape the original variables had. They could be uniform, lopsided, totally random. It doesn't matter. As long as you add enough of them up and do our little centering and scaling trick, their sum will behave like a standard normal variable. This is a total game changer because we know everything about the standard normal. We can just use simple lookup tables to find probabilities for what were once incredibly complex, impossible to solve sums.
And that is the ultimate takeaway here. The central limit theorem is like a universal translator. It takes the messy, complicated, often unknown world of summing up random stuff and turns it into the simple, predictable, and solvable bell curve. It's how we find the signal in the noise.
This one elegant idea connects so many seemingly random events all around us, from the stock market to patterns of rainfall. It shows us there's an underlying order hidden in the chaos. And now that you know the secret, you're going to start seeing it everywhere.